Hi, I'm Saket Dingliwal, co-author of the paper Covariate Distribution Aware Meta Learning, accepted to be presented at 4th Lifelong Learning Workshop at ICML 2020. This work is a joint effort of me and Amrit, advised by our advisor Barnabas. As you might already be familiar, meta learning involves a task distribution from which both trained tasks and test tasks are sampled. We are given very few, maybe 3 or 5 training points per task, and the goal is to learn a classifier or a regression function for a test task. While most of the prior works focus on learning a prior over p of y given x, in our work we learn the prior over both p of x and p of y given x, and then use the inferred p of x to better estimate p of y given x. Moving on to our motivation for doing so. Here is an example of a meta-learning task, where each task comes from one of the 4 hypothesis classes: sinusoidal, linear, quadratic, or tangent. Within each hypothesis class, we have the parameters for the hypothesis class are being sampled uniformly, and so we construct this particular task distribution. And the goal is to regress on a response variable y given a new task using only few of the x as given training examples. Note that in this example, the choice of hypothesis class is not independent of the choice of x. This can be easily seen because here, let's say x, when it is chosen uniformly from -10 to -5, the hypothesis class is sinusoidal, while when the hypothesis class is linear, the x is chosen uniformly from 1 to 2, and so on. Therefore, for a new test task, first modeling p of x can help us to identify the hypothesis class from which it comes from, and then we can better infer the regression parameters for this particular task. And note that the advantage of using p of x is not limited to this example or regression in general. For example, like many semi-supervised methods, which essentially model the unlabeled data and hence model the covariate distribution or the p of x, have better generalization power in low data settings in many of the image classification tasks in many of the recent works. So in this work, we intend to transfer the benefits of modeling p of x to meta learning approaches as well, which haven't been tried and done before. Moving on to how do we do this? We use Bayesian framework to model task agnostic meta parameters theta and task specific latent variables zx and zy. Again, to highlight the key difference between existing approaches and our approach, we have this dependency from zx to zy. This particular dependency signifies how p of x influences the variables p of y given x. Moving on to how do we use this theory and motivation to construct a practical meta learning algorithm. For each latent variable, we introduce variational parameters and maximize the elbow bound. As any meta-learning algorithm, our algorithm also consists of 2 loops: inner loop for task-specific variational parameters, which use the support set, and the outer loop for task-agnostic parameters or theta, which use the query set. For our case, inner loop has 2 parts. First is inferring kappa, the variational parameter for zx, and then using the optimal kappa to sample z of x, and from which we can inform the covariate dependent initialization for z of y, then we use, as any of our prior works, we use SGD to infer values for the variational parameters lambda for the latent variable zy. Coming on to how well we perform, we consider 2 synthetic regression datasets. In one of them, we designed to have a correlation between the hypothesis class and p of x while keeping them independent in the other. For both, we construct the dataset using different hypothesis classes like sine, cos, or their combination. We find that we perform significantly better in the MSE metric over our baselines when there is a relation between p of x and the hypothesis class, and while we perform almost well or equally well to those when there is no such relation. This encourages us to test our approach on real-world datasets like mini-ImageNet in future. Finally, I would like to mention that we have formulated an algorithm inspired by the use of covariates for meta-learning tasks. We provide formal proofs for all our loss functions in the Bayesian model that we have proposed, and we achieve initial promising results on synthetic datasets. So please read our paper and contact us if there are any questions. Thank you.